So without further ado, I'm going to say welcome to the meetup, Danny Ma. Thank you for joining us. It's been a long time coming, so I'm very happy to have you here.
Thank you so much for having me, Dimitrios. It's been really a pleasure to just kind of have a chat with you and also to share some of my experience with everyone who's watching. I hope you guys can get something out of it today. If anything, I just want to demonstrate how all you really need to be relatively successful in this field is just to have a lot of passion for what you're doing and to kind of stick through there's going to be sticking points, there's going to be struggle, there's going to be really difficult things to try and tackle, but just have the great mindset and persistence to go through it, trust in the process, and you will definitely make it.
Oh, that's awesome to hear. Yeah, the inspiration that I needed on my Thursday morning. So,
of course.
Let's jump into it. And I just want to ask, first off, how did you get into data science? And then how did you make the transition over to machine learning engineering?
So, yeah, one of my taglines before was that I've had pretty much almost every single data role in the industry. So I've gone in from when I was doing internships, I was doing data entry. So I was manually just typing stuff into Excel.
Oh, that's a lot of fun, right?
Yeah. Oh, it was amazing. My typing skills went up, but not much else. And then from there, I joined as a data analyst as a graduate. I started working on campaign analytics, did a little bit of predictive modeling, did some digital analytics, worked really closely with great DBAs and data engineers. Then I started working within a proper data science role where I was doing machine learning, predictive modeling. And then once I built my first models, then I was also tasked with putting them into production. And that was my first glimpse into some of the machine learning engineering techniques and some of the tooling that we use currently. And yeah, in my latest role, I've moved over into the real dark side. And yeah, I've just been working fully on the cloud, working with the data scientists to try and productionize some of their models, and also working within a very challenging data engineering space as well. I think, yeah, a lot of people usually think of machine learning engineering and data engineering as kind of two separate beasts, sort of. But then once you work on larger end-to-end projects, you see that they go hand in hand. You almost need knowledge of both to be able to deliver things end-to-end.
Oh, that's such a great point. And that is something that we've had Dan on here, another Dan, not you, obviously, but he, Dan Sullivan, he talked to us basically about how interesting it is and how important it is for a data scientist to know a bit of data engineering and have that like tool in their toolkit to be able to draw on when they need it. And what he said that I thought was really nice was that it's like having, going from a hacksaw to a chainsaw. When you know that kind of information and you can have a bit of a better idea of what data engineering can give you, it will give you that power up and that level up that you can look forward to. Yeah. So I love everything that you say. I want to let you get into it. I know you've prepared some stuff for us. Before you jump into that, though, I just wanted to ask about this productionizing and when you're going into the different tooling, are you working mainly with like third-party tools? Are you building it all yourself? How does that look?
Yeah, so in my first foray into machine learning engineering within the bank, a lot of the tools that currently we use extensively, like the Kubeflow, MLflow, all those things didn't really exist back then. So we manually built a lot of those toolings within the bank, which was really fun. I think, I was one of the lucky ones who had the opportunity to actually go from like almost ground zero and build everything from scratch within there.
Wow.
And it was quite fun, quite challenging because I personally didn't come from a software engineering background. So it was super challenging for me. I picked up nearly everything that I know now, like on the job. I had my education was in actuarial studies, so a mix of business and statistics. So I had a reasonable grasp of the maths and the different like some thinking, probabilistic thinking, and things like that. But outside of that, I didn't really have much more to offer from a technical software perspective. I like to think that I'm okay at solving problems. So every time I look at a code thing, it's literally just, oh, how do I solve it? Where do I find the information to solve it? I can ask people who have done this before, who are doing it at the highest quality. Oh, that seems like a good idea.
Which is why we're here with you today.
Oh, I'm flattered.
So
I can only share what I know. I don't think I'm the best at what I do, but I love teaching others. So hopefully that comes out, the passion.
Nice. Now that is an incredible statement. Before Kubeflow and MLflow were even widely adopted, you were building your own tools. And that had to be...
I'd say it's probably stretching it to say we were trying to build the entire stack or anything. But I think we built most of so data ingestion, working with different systems, optimizing the SQL and running all that sort of stuff. The feature engineering, I think the first models that I built that were used in production were actually done in R. So we Dockerized that, deployed it on one of the servers, and there wasn't any monitoring, proper monitoring. So we were literally just looking at like big cron tabs, making sure that nothing was failing.
Wow.
Hacking around the networks to actually send you an email if something went wrong. It was good fun.
That's incredible.
Like the dirty hacky work that you see when some of the machine learning teams are starting to think about how to productionize some of their things. I've gone through most of it.
And shout out to anybody. Shout out to anybody still using R.
Working hard. R is great. I always suggest it to people who come from an analytics background or are more familiar with data and analysis, like maybe statisticians as well. I actually learned Python first because I thought when I was starting, everyone said, "Oh, you need to learn Python because Python's the best." And then I'm like, "Okay, cool." I learned the Python, so I started learning the Python. Then in my first actual data science role, everyone was using R. That was the only thing that was supported in the bank. So, yeah,
I had to go back and learn that.
Yeah, it was fun. I found after learning one thing, I would just keep translating back and forth between the two languages, and then every now and then, when you use a lot of data, you just always I usually default back to SQL. So all the group bys and all those other window functions. Then mostly the things that are in other languages are just translated versions of the SQL. So, yeah.
Awesome, man. So now, can you walk us through what you have prepared? And I know you've got some cool tech going on your side.
Yeah.
You've got some great screen sharing. Look at that. How cool is that? There he is.
Yeah.
Right on.
Okay.
So I'll let you have it. The
All
floor is yours.
So awesome. Thank you so much. Thanks for everyone who has joined us. So for today in the meetup, I thought I'd try and make some slides so it feels like a real meetup, as though I'm presenting, but feel free to jump in with any questions. And me and Demetrius will kind of have like an ongoing dialogue whilst I'm presenting this. So think of it as almost like we're doing a knowledge sharing, where it's just one-on-one, but you guys are watching. So I think for today, what I wanted to focus on, one of my passions, especially around the data and the machine learning, is experimentation. So I wanted to help you guys understand from an MLOps perspective, and just more in general for the machine learning, what do we mean by experiments within this space? And then from there, it kind of ties on to the glorious target variables. So most of my experience has been in supervised learning. I like to think that most of my expertise is in that space as well. So I'll talk through some of the ideas that you can use, that most data scientists will be using to generate their target variables, and how it has an impact, especially from an MLOps perspective. What downstream impacts does it have? What sort of upstream considerations should you also have when you're trying to generate your target variables from the data? And that also then flows into your business applications of your machine learning models and how you would run actual experiments in production, or even when you're doing it before production, you're trying to do your proof of concepts. We'll try and keep it really relevant and simple with very simple ideas. And I think we're going to try and do like a prediction of someone who purchases something versus someone who doesn't. So nice and simple. We can also
useful.
ad lib and have different. Oh, what was that, sorry?
And useful also.
Yeah, I think if we can try and focus on those problems which cover like 80 to 90% of what we do in the industry, it'll give you guys a much better idea of how you can apply it to these problems, which will most likely show up at work, and then kind of give you some build up your intuition for how you can apply it for different problems. Great. So that's the summary for today, the Cliff Notes. We'll probably summarize this in like a TLDR in the post or something. So now let's talk about experiments for MLOps. It doesn't have to be MLOps. It could just be like or machine learning in general. So when we think of MLOps experimentation, you have your MLflow and Kubeflow and some of these technologies where they've got inbuilt experiments where you can run with different hyperparameters. You can also try different algorithms as well. Maybe you'll have different processes for doing your feature engineering. And of course, you can also change your input variables of the labels and the target to determine what you're going to predict and what your machine learning algorithm will actually learn. So the hyperparameters, I'm not sure if you guys are familiar with all the different ways that you can tune your machine learning models, but essentially you'd have grid search, where you manually input some different values in a grid, and your algorithms can kind of run through each one, train those models, and then you'll do model selection by choosing the best model with the lowest error or the highest ROC or different metrics like that. In the same way, you can also do random search. So very similar to the grid, but you initialize with random points. So if we think of this as the grid, sorry, I didn't realize that my head is blocking that box. What I'm going to do, so say there is this grid here. If you do the grid search, you kind of get these dots in between. So they're very defined in terms of the search space. And if you're lucky enough, you might find the local minimum or maximum where you're trying to find that best model. But probabilistically, it's more likely going to be in these random areas. It generally won't be in those set hard criteria for the hyperparameters. So what we like to do in practice is actually kind of imagine this is the grid, and we'll just randomly kind of do this. And computationally, it's relatively cheap because you can parallelize it quite well. So in general, we would typically go with random search as your best, like your Occam's razor, the simplest choice. What you could do also, so we can also do, I think in some of the technologies now, we have Bayesian hyperparameter tuning as well, where it kind of does a sequential search for the best set of hyperparameters, and each subsequent run for the hyperparameters will search within a space which has a higher likelihood of having that maximum or the minimum to optimize your model. So I can probably talk about this for a bit longer, but in a nutshell, hyperparameters and the way you choose them, you can think of them as experiments. So the different methods as well as the different values that you use to optimize. And in the same way, we can also do it for algorithms. So you guys must have heard of any of the deep learning, the TensorFlow, the Keras, GPT-3 or different things like that. I don't know if we can use that within the thing anyway, but there's all these different algorithms that you could use for your machine learning task. There's deep learning. You could have just your regular logistic regression, something simple, and any of the other operators that we have within those machine learning frameworks we can also use. So maybe if you're trying to predict a certain problem, you can just swap out some of these different algorithms and compare them, and you choose the best model that pops out the other end. And now when you think of the feature engineering, usually in machine learning, we'll always have the input data, and we use that to learn the different relationships between that data input and the target variable. We can also update and change and experiment with different types of features and information that we're passing to these algorithms. So we can have different steps within the machine learning pipeline to generate these features. I'm not sure who's familiar with the different pipelines like sklearn or sparkmlib or different things like that. But you can definitely create different pipelines to create your features. So you can experiment with, maybe you might have call it feature set 1, where you just have really simple features. And then maybe feature set 2, you have things where you might have polynomial combinations or various different things and transformations, log transformations, maybe add some features together, all these different things that you can experiment with. These can also be considered as experiments within machine learning.
Can you go into what a polynomial combination is a bit more?
Yeah, so that literally just like came off the top of my head, but
Nice.
so I'm going to draw down here. So I draw down here. So imagine you have your features. You might have, let's go column A, B, C, D. So if we're going to do like a polynomial transformation, let's just say we're going to do a quadratic, for example. So maybe if you're going to do that, you might have a feature which is a squared, b squared, c squared, maybe d squared. Maybe you have other things like ab, so combinations of the two, ac, ad, etc. Maybe you have cubics as well, so you can have a cubed. But these things, I drew off the screen. But these things, it's all down to experimentation. Some of these work with different algorithms in different ways as well. If your features are still correlated, it still doesn't work. You still want uncorrelated features when you're doing your machine learning. So I think this is more of like the art component of machine learning.
And could you give us like an example of this in the real world, we could say, when you're actually doing it and putting it into practice?
Yeah. So the one that I've seen, like the textbook example of this, is trying to do like a house price prediction. I'm trying to remember the exact example, but let's say you're trying to predict like Boston house price or something. They could try and multiply some of those features together to try and get a better representation at different points of the space. For example, maybe some of those really expensive houses, if you multiply out the number of cars that you have in the garage, how many toilets you have, all of those things in some sort of combination, it might provide you some more insight. And you kind of get these, I'm trying to find the right word for it, but it would be kind of like nonlinear data, as opposed to just looking at the number of rooms, the number of toilets, the square meters of something. Trying to get different combinations might give you a better understanding of the space. And this is, in a nutshell, what some of those deep learning algorithms do anyway. So kind of look at all those different combinations and blow it up into higher dimensions so you can learn more from it. But the downside is they're a little bit harder to explain and understand exactly what's going on. Yeah. So think of this as like the manual process, which most of those deep learning, all the different layers kind of do that in this non-linear space as well.
Awesome. Thank you for that.
Cool. That's all right. Yeah, so features are very important. So of course, they're the thing that your machine learning classifier learns from. So let's say, for example, we have these A, B, C, D features. Maybe in another experiment, you might have features from like E through to Z or Z. What do you guys say, Z or Z?
I say Z,
Z?
but that's because I'm from the US.
Yeah, yeah. But for example, you can try different experiments with more or less data. Maybe you want to try and run other examples where you're going to remove some correlated features. You run some other processes to remove those correlated features. Maybe you remove some with lots of null values or things with high cardinality. You can try one hot encoding versus log odds encoding versus, I think there's another type of encoding using Fisher information criteria split, which is pretty cool as well. But yeah, there's all these different things that you can do to try and massage your data into a different group of features that you feed into your machine learning algorithm. And traditionally, this is what data scientists would be doing. But now that we're going into a world where you kind of, yes, your data scientists can kind of live in a sandbox and do all this stuff and find the best thing that worked from that small blast radius proof of concept. But then the question would be, how long will it take to put that into production? And it's from my experience, it's kind of, we're moving towards a space where if you have all your data in one place and in the right production pipeline, all your sandboxing and your experimentation should be done within this production framework. So then if you need to really flip it into production, you almost just need to flip a button, turn it on, and then it'll start running.
Yeah, completely. Like what you would expect it to do, right? You don't want to be held up by this because you have to change everything from one environment to the next, or it just doesn't seem efficient that way. So having it be where you're doing all of this with the end game in mind, it seems like the right way to go about it.
It's logically and from an efficiency perspective, you can't really argue against it. The only issue is probably in the current scenario, not too many companies have the maturity to actually have all their data in one place, have their data engineers and machine learning engineers and data scientists working together with the business to actually get all these business processes to feed off some of these machine learning outputs. It makes it really difficult to actually tie it all together. So I think it's a maturity thing. It'll come in time.
That I think we've heard so much on this meetup. And so I just want to kind of derail you real fast. We'll get right back to this. Yeah. Is there some things that you've seen that you could say the maturity is not there because of this or that? Like if I'm a company, how can I become more mature?
So I have to think of my words carefully in case I inflame someone. I think a lot of the time where I've seen some businesses really struggle with this, on one hand, usually they're really large. So there's just lots and lots of silos. The production data means different things for different people. For some, it could mean it lives in Excel spreadsheets that get delivered on a regular cadence. For others, it could be it's only Spark. For others, it's only Kafka or streaming or whatever. So I think it's a little bit of a mismatch in between the levels of data, more like it would be data engineering know-how across the different groups within the business. And there's usually, for large businesses, there's never really one overarching strategy. You just see lots and lots of, like each group will have their strategy, but there's nothing that really ties them all together. And even if there is, that's usually like a huge transformational thing that just takes years and years. And by the time you get close to delivery, who knows, like maybe the leadership has changed and then the new guys that come in, then they could just change everything because they don't like it.
Yeah.
And Yeah, it's kind of crazy when you think of it and from like a cost perspective, because these processes cost money, like huge amounts of money. There's all this, you see the cloud transformation, the just moving from one provider to another, even on premise, is they're usually multi-million-dollar projects, like 2 to 3 years time, and they're just massive monoliths, just moving very slowly as well. But they're difficult if you have lots of data and yeah.
Yeah, and I thought it was insightful too how you said not only is it the teams like these data science teams, data engineering teams, but also the business side too. Everyone needs to be looped in, right? So that you're getting the right information, you're getting the right data, and you're actually solving the right problems.
Yeah, almost 99 times out of 100, where if you've seen some machine learning project that misses the mark, it's nearly always down to they weren't solving the right problem, or they're trying to build a model for something, but they couldn't tie it back to the business objective, or they couldn't measure something. It's always the case. It's never really about, oh, your machine learning model was off by 0.1 AUC, or that 0.1 AUC is quite large, but 0.001 AUC or whatever it is. It's always down to how you apply it and just the know-how and experience to kind of avoid some of those pitfalls is the most important thing.
That's awesome. All right, so a little bit of a tangent there. I'll let you get back to what you were talking about. Yep. But thank you for entertaining my questions.
Okay, so we're still talking about experiments for the machine learning. So we talked about the hyperparameters, the algorithms, as well as the features that you can experiment with. But one of the most important things that you should be experimenting with is what we call the labels or the target variable. And this is purely within a supervised learning space. But usually you think of this as the column that you do not share with your machine learning classifier, because if you give it to it, it learns exactly what it is. We call that feature leakage or label leakage. But usually you'll have a data set that looks, say, like this. This is all your columns and your rows. And what we want to do is probably hold out that final column or whatever. And you can think of that as your Y. You know, in the maths, when people go like, there's a model that has X, and then you try and fit the model, the f of X equals the Y. And then you try and build that mathematical model to try and make that prediction. In the same way, the machine learning is doing exactly that, where it sucks in this thing and then tries to predict this thing. And that's like machine learning in a nutshell. That's all it really does.
Yeah, it's not hard. No, that's totally understandable.
Yeah, I think, yeah, maybe too many people think of machine learning as this amazing ivory tower thing where you've got like crazy people hacking up all sorts of things and it's really difficult. I think for this community, for the MLOps community, it's probably less like that, but it's definitely, data science really has this mythical nature from probably on LinkedIn and all these different places where people just think data scientists are really amazing. I'm here to almost debunk that and just say, no, this is, anyone can learn this stuff. You just need to want to learn it.
Yeah, a little persistence goes a long way.
Yeah, definitely. Okay. So now I'm going to talk about how you can update and change these labels and target variables. This might be a little bit abstract, but bear with me. But when we think of the target variable, usually in, let's say, the data set, let's say this is your Y target variable, and we're literally just going to go whether something is a positive or a negative. Generally, you see this as either ones or zeros. And the way, so you guys might have experienced Kaggle competitions where you always get given the target variable that you're trying to predict. In practice, working as a data scientist or machine learning engineer, you usually never get this. You have to figure out some business logic to generate it. And And nearly, I would say, 90% of the time, this is purely SQL or some variant of it, some Spark Scala or something that you're using the data. It can also be done in an R or a Python or any other language. But majority of the time, you can do most of the label generation within pure SQL. You'll, like the times where I've had to build labels, we had to join lots and lots of different data sets and tables from different databases, handle some of the effective and expiry dates for some of those slow moving dimensions and all these different data modeling aspects of getting the data right, which is, it's probably its own separate topic as well. But just, trust me when I say getting this label right in practice is the hardest thing, but it's also the most important thing. You could have a really great label and just throw in a lot of really good data or even average data, and it still outperforms something where your label is totally wrong. So it's super important to get this right. And I believe it's teachable. You don't need to have actual hands-on experience to learn how to build this label, but it does help, of course. So in saying that, some of the things that you have to keep in mind for this target variable is, I'll just list them out here, is timing, bias and drift, imbalanced classes, and also how you split out your train validation test data sets. So let's talk about timing first. So I'm just going to rub this guy out. So when we think of timing, let's go, one of the simplest things is probably, let's try and predict the probability of someone doing some event. And usually that's where people stop. So let's say the car insurance is really popular. So people would like to say, oh, let's predict which one of our customer base is going to lapse in this period or something. So you get this Y variable is just this thing where you get people of 1 or 0 again, of whether they lapsed. But you should be asking yourself, when do they lapse? When during the year? When is this 1 and 0 actually set? And all these other questions, which there's no real statistical concepts or technical concepts. It's literally just logical thinking. So that's another thing for anyone who doesn't have the math and stats background. You kind of don't need it to start applying some of these things and thinking through some of the problems. So what we like to think of as practitioners is usually, okay, what's the probability of some event happening in the next N period? So this could be T days or T time or whatever. But when we think of supervised learning problems, in general, it's much easier to think of it within a time-bound problem. So, for example, when we try and run these things in production, you want your model to kind of give you out, this is the probability of Dimitrios lapsing on his car insurance account in the next 30 days or something like that. So then when you use that information to actually do something about it, then you can have some really actionable insight. So if I know Dimitrios is going to lapse within the next 30 days, and he maybe has like a 90% probability of doing that, what should I do? Maybe I could be more aggressive and I offer him 50% off just because I want to keep his business. Maybe you just give someone, you call him just to catch up and see how he's feeling, if everything's all right, and then try and get a good sale out of him. There's all these different things that you can do from a marketing perspective. But these things, when you think about the machine learning, my light has switched off. Sorry, so it's a little bit dark. But these things from a machine learning perspective are super important because, and especially from the target variable, because you need to think about how it's going to be used once you build the model. So timing is super important. I think one of the key things is just being able to know the timing where you'll be able to action some prediction. So within the marketing space, 30 days might be okay. Let's say you're working in heavy industrial machinery, maybe you only get 1 minute or less to actually do something if you're trying to predict a catastrophic failure, for example. Yeah, I think this is where machine learning gets really interesting. You can apply it in many places, but it's definitely not a one size fits all for all problems.
Such a good point.
Do you have any other questions so far in terms of the timing?
Well, I think it goes back to that whole business value, right? And feel free if anybody else in here has any questions, drop them in the chat. But for me, it always comes back to that, like, yeah, asking the timing of when an event is going to happen then gives you insight on what you can do about it from the business side of things. Whether it's the marketing thing or it's, okay, there's going to be this catastrophic event in the factory, so we know just to shut everything down, or we know to do X and potentially evade that big catastrophic event, right?
Yeah. And yeah, I think from a practitioner point of view, it's you could build the best model, but if the thing that you're predicting is not the right thing and not applicable, then it kind of doesn't matter. It doesn't matter how good your deep learning and hyperparameter optimization skills are if you can't use it to actually make a decision.
Yeah, again, it's so funny you say that, because Dan Sullivan, who I referenced before, mentioned the same thing, how one of his biggest, I asked him about a war story, and he said, one of my biggest war stories was just, I spent months on a model, tuning it and getting it to be the best, and went back, and the people that actually were using it for the business value said, we can't use this. This doesn't do anything for us. And so he was just like, they didn't care what did he say? Like, they didn't care what my F score was. And he was so proud of his F score. That was so good. He was like, wow, this is great. And then he goes and gives it to the business side of things. And they're just like, what are we going to do with this?
Like I've seen a few meetings in my time where data scientists, they're really smart people, like with PhDs and really, really intelligent, and they're trying to explain an ROC curve to a senior executive, and you just see the glazed look, like they're gone, and they just have no idea what they're talking about, and they kind of just miss the mark. And then the whole point of that meeting was to try and explain the results of the model or anything that they were using, and the executives just kind of came out of it with like, do these guys really know what they're doing? Like,
so the whole point there is really to be able to, as a data scientist, I guess, to be able to show your worth and boil it down into this, like, simple to digest. Hey, we can tell when someone is going to churn, or we can tell the probability of this happening within the next X days. So we suggest that you do this about it. Or we suggest marketing takes a deeper look into it and puts them into a sequence or a different newsletter, whatever it is.
Yeah, and it's nearly all the machine learning has to be about application. Definitely.
Yeah. Sweet. So what do we got next?
Yeah, so timing is very important. I could probably, if you have me on another time, I can go through all the different methods that we can try and do the timing in a statistically valid way, but that will take me 2 hours, that by itself. But another thing that we can talk about is the bias and the drift. And this kind of, they're two separate concepts, but when I think of bias, it's also linked back to the timing. So if you think of that lapse, the insurance lapse example, if you, let's say you choose the date of the actual event for the date where you're going to use for all your feature generation, because another thing to keep in mind is, let's say your date of your label is here, and let's say 2020 0101. When you choose that as your label date, you have to get features from the past. You can't get features from the future. That's a no-go. You can't predict, well, you don't have future data essentially. But the next thing for the bias is also very related to the timing, because let's say Demetrius is this example and he's lapsed, and he lapses on that date. He lapses on like 2020 Jan 1st. If you use that as your 1 or 0 metric, like that 1 or 0 label across all your customer base, what are you predicting? You're predicting the probability of someone lapsing today. And it's not really usable, is it? And you're bound to get a lot of noise as well, because maybe you'll pick up all the different activities that Demetrius was doing before that lapse event. Maybe you won't. I've seen other ways that people try and generate this date for that training example also, which is different. So let's say, I probably shouldn't go into this too much because this is part of the 2-hour topic that we could talk about. But
if anybody wants to, you can check out his YouTube channel.
Yeah.
And he goes way into the weeds there.
And but yeah, essentially bias is more around bias in terms of when something happens. So I guess it's also tied to the timing as well. But when we think of the drift and the bias together, you can kind of think of it like, let's say there's a timeline, and this is, say it goes all the way from 2008 up to 2020. Depending on what records you want to include in your machine learning problem, do you have any, like, let's say the data from 2008 up to 2012, this is, let's say, GFC period. Do you think that will be very different to post-GFC period? And then from 2020 to 2022, do you think there'll be some COVID-related data that's baked into your context, and whether that will also impact your prediction task as well? And these are they're very external context things. But when you think of people's behavior in the data or the different things that you're trying to predict, if it's a consumer behavior pattern or a banking or retail or anything like that, of course, these economic factors will definitely play its part. If it's machinery, maybe it's not in such a large time factor, but maybe the temperature of the seasons, the rainfall, humidity, all these sorts of things might play a factor as well. So these are things that you kind of, over time and domain experience within the different areas, as a machine learning practitioner, you develop stronger intuition for when these might impact the actual problem. But when you think of it, these are not technical issues. These are thinking issues. They're logical problems. So just having the knowledge of how you might handle some of these situations, yes, that might be technical, but knowing that these situations might occur because of the scenario and the context, that's business knowledge. Okay, so bias and drift, very important as well. The third thing to think about is imbalanced classes. So in Kaggle or some of those different machine learning examples, normally you see most of those examples will have 1-to-1 negative to positive ratio. This rarely happens in practice. You might get, if you're really unlucky, you might have 0.001% of positive cases, and the rest is all negative cases. So it's a real rare event prediction. And there are different ways to handle imbalanced classes in terms of how you would do with the target variable. So there are different things. I'll just list out a few different techniques here, but you can always downsample the majority class. So let's say 0.0001% is a little bit too low, but let's imagine that it's 10% is positive and 90% is negative. To get it closer to that 1-to-1 ratio, you could potentially downsample this 90%. And you just take, 10 divided by 90, or you try and make it match 1-to-1 with the positive case. Another example, or another technique that is very popular these days is using something called SMOTE. I forgot what it actually means, but it's kind of upsampling the minority class and kind of using the statistical distributions of the data to generate fake data, so you can also learn from it. And it does the other way around, so you're oversampling the minority class. There's other techniques, so these are kind of simple techniques. The more advanced technique is to actually update the logic itself to force more positive cases into your data set. And that ties in really well with this train validation split. So what a lot of people think of train validation split, right? So maybe I'll ask Demetrios to find out. Have you ran any examples where you just get given a data set, and how would you use that to split your training validation and your test sets? What sort of techniques would you use?
I actually will defer to the practitioners in the chat on this one, because I'm not sure I have any good answer. Does anyone in the chat want to let us know what you think?
Might be a difficult question.
We'll see if anything comes through for now. Otherwise,
but yeah, I'll probably keep barreling on. But
yeah, let us know. And if something comes through, random, we got one.
Oh, bingo. So nearly all the time, people would just split this into 60, 20, 20, or different things. Maybe you might not even have a test set. You might only have a training and a validation set. Maybe you do k-fold cross-validation, where you have you split your data set into k parts. You train it on k-1, and then you validate it on the remaining part. There's all these different techniques that you can use to improve your model prediction by kind of learning from the data as much as possible. In practice, this doesn't always work as well, as always. In practice, what we tend to see is that, so let me go back to what the training set and the validation set and the test set actually does. What are their functions in machine learning from a purely theoretical perspective? So when you think of the train set, so let's just say we just randomly split the data. So I've got my train set here, validation set, and the test set here. So I think we're all in agreement in that this test set, we just kind of leave it there. We don't do anything. And for the training set, this is where we kind of, we want to do all the different transformations, the feature engineering, build all those pipelines, and then eventually run the machine learning algorithm on this training set. Where this validation set comes in is, I'm not sure for what people do these days, but when I was learning, we would always run our algorithms and use the validation set as an early stopping criteria. So you can think of the algorithm just keeps running and running on this train set, but after each iteration, it would actually go and test that data or test that model on the validation set and return you some metric, say AUC, for example. And you can set it, you can make your training routine continue until that AUC metric kind of stops improving. That's why we call it early stopping. So that is what I used to apply, and I would still apply now. I don't know what people do now. They've got all this crazy stuff that goes on. But when you think of the training set and the validation set and the test set, there are some logical components to that validation set and the test set. So let's say most people, when you think of these training, validation, and test splits, it all comes from the same data set. So you just get this block of data, like a data frame, and then you randomly split it. In practice, if you randomly split data across different time periods, you could inherently learn something or learn some sort of information from the future and use it to predict the past. And one of the ways that we avoid doing that is to do out of time training, validation, and test split. So going back to this GFC example, maybe we would use, maybe that's not a good example. If we have another timeline, so let's say this is just 2016 through to 2019, for example, maybe we would use the first 2 years for training data, so up to 2018. And then we split the last year into 6 months and 6 months, maybe. And this is assuming that you don't have funny things going on throughout the year. If you have funny things going on throughout the year, maybe it's safer to actually go at a year rate for your training and your validation. Or maybe training can have more data, but your validation and your tests should be the same split size. And when we think of the training, validation, and tests, when you think of the distribution of the data, what I was always taught was your validation and your test set. So these two guys, so this validation and that test, they must come from the same distribution. Otherwise, you have no idea what you're optimizing over. And that's like some could consider it a technical thing, but it's almost just logical. So if you're training your machine learning algorithm and you're iterating over the training set and you select the best model with that early stopping criteria based off that validation set, you really need to make sure that whenever you're stopping it, it matches to the thing that you're going to test on, which is the test set. So I know there's a few mental hops in there, but it's all very sequential. So do you have any comments on that, Demetrius?
I was just seeing that Laszlo was putting some stuff in Slack. I don't know how long ago it was. I guess it was a while ago, Laszlo. Sorry, I'm just seeing this because I've been monitoring the chat here, but not the Slack. So I'll say, I guess this will be catch up. Then he's just mentioning that when he worked in finance, if the data is on premise, then it is in sample. You can only do out of sample with data that doesn't exist yet. That was his thing when he was working in finance. I don't remember where that was from. Maybe you have a better memory than I do. Laszlo, if you want to put in here what you were mentioning.
Yeah, I think, in sample, it's still, definitely you can still use in sample data. I think from my experience, I've always used this out of time testing because I'd always be running these models in production to try and predict something ahead, which I think that's what Laszlo. Yeah. So for out of time, it's very useful if you're trying to predict something in the future. Sometimes for machine learning models, all you need is to try and understand and predict what happened in the past and try to say, in the past we could predict failures from this point in time or whatever had X and so metric, which is all good also. I think the out of time and doing the predictive modeling for behavior, you really do need this out of time testing. I know that a lot of people just kind of they just bash it all into the same data set. It does work, but there are implications in how testable it is. So the only way to test it is to run it in a live environment and then see what happens. And I can talk about that for days also, but there's a whole forward testing regime that we can do with our models to make sure that they're doing the right thing before we even go live. And that's even when you have your training, validation, and test splits, there are still more things that you can do to validate that it's going to work before you actually go live with it and potentially risk pissing off some customers or something.
Yeah, totally. So I want to be respectful of your time. I know we're just hitting the top of the hour. Do you have 2 minutes or 3 more minutes to wrap it up for us and give us?
Yeah, I can. So I'm more than happy to go for as long as you want. I think
Nice.
I'm up to slide 3 of 7 or something. So I just ended up talking way over time. I must be respectful of your time also. So
well, I think this has been great, man. This has been super exciting and interesting. And for me, of course, like always, when I'm watching your stuff, I've learned a ton, and it helps me understand things. You have an ability to put things into a very simple manner, and it's, again, it goes back to that distilling down these very complex concepts to share to people who aren't necessarily doing this day in and day out. And you're able to do that because I'm one of those people that is not in the trenches, right? But I understood what you were talking about, and I learned a ton from it. So maybe we do the 2-hour deep dive on your YouTube channel, and
I think so.
Yeah, I think it's really cool for everybody that is out there and has not checked out Danny's YouTube channel. Go have a look at it if you want to learn more. He's doing all kinds of cool stuff with learning data science, and obviously you've seen from up until now, he's got an ability to teach, and he has a lot of knowledge that he is very generous imparting onto the rest of us. So is there anything else that you want to say just before we go and to kind of wrap it up?
I would say probably for the MLOps community. I know there's a lot of focus on tooling and model serving and working closely with the data scientists to make sure that all the processes and operations are all good. What I would like to stress for all the machine learning engineers out there is to kind of challenge yourself to really understand where the outputs are being used, especially in most places, you don't really get a chance to determine what business processes it actually changes or the different decisions that it gets to make, unfortunately. But it's definitely nothing is stopping you from learning about it and getting that contextual understanding of where your work is being applied. So I think that's super important and very valuable. It also helps when you're writing stuff in your resume and you can say, oh, my outputs help deliver X million of dollars of revenue for marketing initiatives or something. But yeah, I think just be as curious as possible. Don't be intimidated by the data scientists talking about all these statistics and maths and whatever. Most of it just boils down to pure logical thinking. Work closely with the data scientists when they're doing the experimentation. Chances are they're not as technical as you are. So there are definitely tons of things that you could share that will help make their lives easier. And hopefully they have lots of things that they can teach you as well from the statistics side and all those other things that we talked about today. But I think, yeah, just be as collaborative and as curious as possible, and just believe in yourself that you can learn all of it, because if I can learn it, you guys can learn it too.
Wow, that's such a good point. And it comes back to that producing real business value, right? That's what we're going for here. And I think you put it wonderfully, because that will give you a level up. If you're always thinking about the business need and the business value that you're going for, you're going to be playing in a different field than just, okay, what's my accuracy score? How can I predict this? Or how can I put this model into production? If you're a machine learning engineer and you're just focused on the pipeline, or you're focused on getting things out, yeah, that's great. But is it something, what is this model going to be doing once it's out? And so really conversing with the people that are more on the business side to make sure that you are producing the most value, because maybe a little cross-pollination every now and again you realize that there's something very simple you could be doing that produces even more value.
Definitely.
Awesome, man.
Value is the word.
That's it. So you have given us a ton of value today, teaching us all about this stuff. I really thank you again. And for anyone who doesn't follow you on LinkedIn, get out there and follow Danny Ma. He's dropping all these bombs on us all the time, every day. And for everyone else out there, thanks for watching. Thanks for sticking with us. And we will see you next week for more MLOps meetups.
Awesome. Thank you so much for having me.
See you guys and girls and everybody.